my dear students. This session will be on windowed scalar multiplication, which is one of the important scalar multiplication processes in elliptic cryptography. So during this lecture, I will be explaining the algorithm that is required for performing the scalar multiplication through windowed scalar multiplication approach, which is especially applied in the elliptic cryptography. In the previous lecture, in one of the previous lectures, we discussed the left to right scalar multiplication process. I hope you are aware of the importance of performing scalar multiplication in elliptical cryptography, because in most of the utilities like key exchange algorithm or elliptical encryption process or decryption process, scalar multiplication is very important process in which a point is multiplied with a scalar. And since this is one of the very important processes, a lot of optimizations techniques are being applied in designing a suitable scalar multiplication architecture, and based on that, a lot of improvements have been brought on defining the scalar multiplication process. One such algorithm is windowed scalar multiplication. In the left to right scalar multiplication process, based on the given bit, the number of doubling operations or number of addition processes were decided. In this particular windowed scalar multiplication process, as the name suggests, a particular window is going to play a crucial role. Let us first understand what is the meaning of window and why it is named as windowed scalar multiplication. The main difference between left to right scalar multiplication and windowed scalar multiplication is windowed scalar multiplication utilizes a lot of pre-computations. That means already we will be calculating some point scalar multiplication, and whenever required, such scalar multiplication product will be utilized during the multiplication process. The very important advantage of this is once you perform the required pre-computation operations, for example, it is going to be fixed based on a particular metric, and after fixing the number of pre-computation operations, whatever be the number of bits that are present in the chosen scalar, accordingly based on the window size, we will be performing the addition process after performing sufficient number of doubling processes. Instead of multiplying with a single bit, now we are going to multiply the the given point with a group of bits called a window. So the algorithm starts with the first step as choosing the window size W. Window size means it's a numerical value, it's an integer. Window size decides the number of bits to be chosen from the given scalar value. For example, if you take a scalar value 255, the minimum number of bits that are required to represent 255 is 8. And if you choose the window size as 3, so 2 full windows can be chosen. That is 3 plus 3 plus 2. The last window, the third window, will not have 3 bits, only 2 bits, because they are all residual bits. If you choose the window size as 4, then 2 windows can be obtained. So if the number is 255, all ones in the binary representation we get. And if we assume the window size as 4, 2 windows of 4 bit size will be obtained. And they will be multiplied instead of individually multiplying with each and every bit and performing the doubling and subsequent addition processes. the entire window multiplication can be done based on the pre-computed values. So this process begins with choosing a window size W, and the next step is, for the given window size, we have to pre-compute AP, that is, A is the the window, a part of window. Totally, if you have 0 to 2 power W minus 1 window possibility. Suppose if W is equal to 3, how many combinations are possible? Totally 8 combinations are possible. And of that, 0 to 2 power W minus 1, 2 power 3 minus 1, 0 to 7, totally 8 combinations are possible, 0 to 7. So for that, what we have to do, 0 into P, 1 into P, 2 into P, 3 into P, 4 into P, up to 7 into P we have to calculate. They are all pre-computed values. So accordingly, for computing 0 into P to 2 power W minus 1 into P, based on our previous understanding of point addition and point doubling process, we must have the pre-computed values. The pre-computed values can be stored in a lookup table after computation, so that whenever required they will be used. This is a very important difference between windowed scalar multiplication and left to right scalar multiplication process. That means we are going to generate a pool of pre-computed coefficients, which is a unique step in the windowed scalar multiplication. And based on this lookup table creation of pre-computed coefficient, a lot of other algorithms have been developed. We can see a lot of variations in the windowed scalar multiplication as its successors. Then step 3 is, now we have pre-computed some values, right? In fact, when we are applying this windowed scalar multiplication for a large number of scalars, then all the possibilities have to be generated. Otherwise, for a single instance, the chosen window values can be selected. So we will understand this particular concept. That means I'm not asking you to create the lookup table for all the combinations if you are doing scalar multiplication for only one case. If you are going to do the scalar multiplication continuously on an online process wherein the scalar multiplication needs to be performed, then we might not have any idea about the type of scalar that is going to come in. So accordingly, all the combinations of pre-computed values have to be stored. Otherwise, if you are going to perform this scalar multiplication for only one value, a chosen number of pre-computed coefficients are sufficient. Now let us come to the step 3. Step 3 is the collection of 2W array. 2W array means, for example, if W is 3, it's a 3-bit values, collection of 3-bit values. If you have a 4-bit window size, collection of 4-bit computations. Like that, we have to generate the n values. So the n values, every time we will be using this pre-computed values during the subsequent computations in the multiplication process. Then step 4 is done only during the start of the multiplication process. That is, we have to just initialize the value. First value we have to initialize. After that, that is nt into p. T is the first element. P is the given point. For the first time we have to just initialize it. After that, we have to add it with nt minus 1, nt minus 2, nt minus 3 till n naught. We have to add it. So that is what explained in this step 5. So from t minus 1 to 0 number of rounds, what we are going to do? We are going to do first doubling process, after that addition process. Now, why do we use this particular method? Any type of architecture, whether it is going to be implemented on software platform or hardware platform, Based on the given platform, the requirements are different. For example, software platform, we will be trying to reduce the number of computation so that the time required for computation can be minimized. So time, I have to reduce the time for performing a given operation. Second one, the number of computation. So the number of computation is reduced. Accordingly, the time will be reduced. So therefore, what we do is we just try to hit the reduction of time by pre-computing the the scalar values. That is the main advantage of this approach. Based on the pre-computed values, every time we are not going to compute the given scalar multiplication during the process of execution of the multiplication. Rather, the pre-computed coefficients will help us really to reduce the time when we apply the scalar multiplication for a number of values. But pre-computations may take some time. So accordingly, we have to analyze the trade-off, right? We want to reduce the computation number of computations. We also want to reduce the time. This is a requirement with respect to software platform. With respect to hardware platform, obviously, if you reduce the number of computation, your time will be reduced. But since we have the pre-computed, it may consume more amount of memory because we are storing something in the memory, on-chip memory or off-chip memory. So pre-computed values require some amount of memory. While in the case of left-right scalar, as all the operations are performed based on the given instance, the memory requirement was not so high in the case of left to right scalar multiplication. So these are some of the analysis which we can do. But the crux of this operation is we are doing some amount of pre-computations. Now, let us first understand this process with a small example, and followed by that numerically let us try to analyze this. This is the problem chosen for understanding this windowed scalar multiplication. For the elliptic curve E211 of 0, minus 4, where a equal to 0, b equal to minus 4, and this elliptic curve can be represented as y square equal to x cube minus 4. Y square equal to x cube minus 4 mod 211 with the g equal to 2, 2. The point is 2, 2, and the scalar given is 121. Now the requirement is we have to perform n into g, right? Now, as the first step says, we have to choose the small window size w. Now for this example, I have chosen a window size equal to 3. Therefore, total number of computations, total number of pre-computations are going to be 0 to 2 power w minus 1. So 2 power w minus 1 is equal to 7. So 0 to 7. And on the other hand, we have to binarize the n value, which is given as 1, 1, 1, 1, 0, 0, 1 base 2. That means it requires 7 bits. Now, all the 7 bits have to be grouped based on the window size chosen. The chosen window size is 3. So I first choose the W array elements from the scalar. The scalar first 3 bits I have to choose, next 3 bits I have to choose, next 3 bits I have to choose. I have to group and form the collection of W array elements. So now this n requires a minimum number of bits, that is, it requires 7 bits to represent 121. Therefore, 2 values with full window size can be splitted, and finally only 1 bit. Actually, we are not going to add any padding or whatever it may be. Even if you want to add padding, you add it as a prefix and not a suffix, because if you add it as a suffix, the value will change. For example, if you want to make one, if you are adding a couple of zeros after 1, the value is completely changing. The value becomes 4. that is 100. But if you add it as a prefix, the zero adding, if you do it before 0, it doesn't make change of value. So 1 can be chosen as such, right? So n2, n1, n0. n2 equal to 111, n1 equal to 100, and n0 is equal to 1. Wherein n2 and n1 take 3 bits each, with n0 taking only 1 bit. Now, as per the algorithm, first we have to do pre-computation process. So, pre-computation process means during the computation, what we do in the left to right scalar multiplication process, either the point will be multiplied with 1 or with 0. If you are multiplying with 0, you do only doubling process and you won't do the addition process. But if you multiply with 1, what you do? You do the doubling process followed by addition process, right? But now, based on the window size, the smaller pre-computations need to be performed. Now, if you look at the given operation, we have to perform 7p, that is 111, which is the decimal representation of 111 is 7. So 7 into p, that is n2 into p, n1 into p. Those are the two operations to be performed, because n0 is equal to 1, 1 into p equal to p. 111 into p, that is equal to 7 into p. 100 into p, that is 4p. What we have only, for example, instead of p, you can assume it as g. For example, this example, we have chosen it as g. So I just change it as g as well here, because it may confuse you with the mod value. So I just change it as g here. So what we have to do now, 2g, from 2g, how do you do 2g? Doubling process, right? 4g can be performed using doubling process 2g, and then 6g. 6g, how do you perform? 4g plus 2g will give you 6g, and then 7g. How do you pre-compute 7g? 7g can be performed by adding 6g plus 1g. So first to 2g, point doubling, 4g, point doubling, 6g, point addition, because 4g plus 2g, point addition. If the 2 points are different, obviously it comes under the category of point addition. If you are trying to add the same point, then same point, it comes under the category of point doubling. And 7g, how do you perform 7g? 7g is equal to 6g plus g. Again, it comes under the category of point addition. Now, just look at the multiplication process. The point g needs to be multiplied with n, because the same example we considered for left to right scalar multiplication as well. Now, first initializing we have to do. What is initializing? 7p we have, 7g we have to perform, right? 2, 2 is the point, 7g, b6, b5, b4. So the first bit is b6, b5, b4, b3, b2, b1, b0. So b6, b5, b4 one group, b3, b2, b1 another group, b0 is a separate group. So first 3 bit n2, next 3 bit n1, last bit is n1. So first we have to initialize it. B6, B5, B4, we have to perform 7G, because as we had already computed the 7G, we can directly use it. So whenever 7G comes in, you need not do the computation process. This is the biggest advantage of Windows scalar multiplication process. So you are performing that. After that, what we have to do? After that, we can go for the next window. First window is over now. Next window is 100. 100 is a 3 bit, right? So we have to perform 3 times doubling process, because it is shifting process. For every bit we were doing the point doubling process in left to right scalar multiplication. Same here. Suppose if you choose window as 4 bit, window sizes 4 times we have to do doubling. So for B3 one doubling, B2 another doubling, B1 another doubling, right? the same pre-computed value has to be doubled. Earlier, what was the result of 7G need to be doubled. 3 times we have to double it. After three times, if you perform the doubling, what we have to do is, already we had computed no 100 base 2 into b, that is 4G. Now 4G needs to be added. This is not 4G, this is again this is 1G. So 4G, after 3 times doubling process, you add it with 4G, right? For that, what you are doing, you are not performing 4G, rather you are just calling the 4G pre-computed value. You are just reading, for example, in the hardware, whatever you have stored in the memory, you are just calling it. So you are not going for any ALU kind of operations for during the multiplication process, right? As I already told you, some memory overhead is required in this particular algorithm. So after that, what happens? So now 2 windows are over. Last one is not a window because it's a single bit process. So the bit value is 1. So what we have to do, we have to just left shift it. That means point doubling, and then one more point addition. For example, if that bit is equal to 0, then we stop with only point doubling. No more point addition over there. Since it is bit 1, we have to perform one more point addition. So let us analyze the requirement. Number of pre-computations 4. That is 2 point doublings and 2 point addition. For 2G 1 point doubling. For 4G 1 point doubling. For 6G 1 point addition. For 7G 1 point addition. Right? So 2 point doubling and 2 point addition process. Now during the multiplication, what we do? So the pre-computation count is fixed. So this may change based on the given value, right? For example, this case actually we do 2G, 4G, 6G and 7G. We don't do 3G, we don't do 5G. So if it is a requirement, we have to do it. So why I have done only 4 instead of 7 possible combinations, I have done only 4 because I have chosen a value which requires only that. If you choose some other value, accordingly the pre-computation may change, right? I hope you understand it. Number of doubling operations during multiplication is 4 because one doubling, again one more doubling, for B1 another doubling, for B0 another doubling, so 4 doublings. Again, at the end of B1, again we do one more addition, and for the last bit, one more addition process. So total doubling operation during the multiplication 4, total number of addition operations during a point addition operation during multiplication is 2. Therefore, total number of doubling operations is equal to 6. So total number of point doubling operations is equal to 4 plus 2, 6, including pre-computation I am telling. Total number of point addition operations during multiplication including the pre-computation equal to 4. I hope you remember same number of the operations were required for left to right scalar multiplication as well. But based on the given value, it may change, right? The important advantage that you have to understand is, if you are performing some other new value sequentially, then it may get reduced because you have already performed pre-computation and stored it. You need not do the computation again and again. That is the important advantage of it, right? So let us first analyze the results that we are getting by solving this problem. So first pre-computation process, computation of 2p, because it is point doubling process, as you know that point doubling needs to be performed when 2 points are same. So lambda for point doubling is lambda equal to 3xp square plus a divided by 2yp mod p, and the x resultant coefficient is equal to lambda square minus xp minus xp mod p, with yr equal to lambda into xp minus xr minus yp mod p. Now xp, the point value, the point chosen is 2 comma 2. So xp is equal to 2, yp equal to 2. Same, xp equal to xq, yp equal to yq. Lambda computed 3 into 2 square plus 0, as a is equal to 0, 3xp square plus 0 divided by 2 into 2. That is 12, 3 into 4, 12, 12 divided by 4, mod 211, 3 mod 211. So lambda value is equal to 3. XR value, by applying into the equation, we are getting value equal to 5. That is XR equal to 5. With YR again, YR equal to lambda into HP minus XR minus YP, right? Because it's a normal point doubling process. So minus 11 mod 211. So 211 minus 11, that is equal to 200. So the 2p, the computation of 2p results in a point 5 comma 200. So 2p, now we generated 2p and we can store it in the memory, or we can store it in some other variable, or a list, or array, or whatever it may be. Next computation of 4p. 4p can be performed by point doubling of 2p. That is 2p plus 2p. Again, I am doing point doubling process. So lambda here is equal to 198 by applying the similar equation as we used for 2p. XR, again lambda square minus xp minus xq, because xp and xq are equal here. See, what was the 2p? 2p is equal to 5 comma 200. Now I am using 5 comma 200 here. See it. So lambda is equal to 198. As you know that this 1 by 400, 400 inverse, for inverse modulo, you have to apply extended Euclidean algorithm. Wherever modulo inverse comes, you can apply extended Euclidean algorithm, or you can use existing online tools, or online calculators, online modulo inverse calculators for computation of that. So if it is a software program, you can call that function to compute the modulo inverse. So XR equal to 159, and now YR equal to 198. 198 was the lambda. Equal to XP minus XR. XP is 5 minus 159 recently computed XR minus 200 mod 211, that is equal to minus 97 mod 211, that is equal to 114. So 4p gives me a value, a point 159 comma 114. Next is 6p. So 6p is again point addition, because 2p plus 4p. So now I have to use both the results of 2p and 5p. 2p is 5 comma 200 and 4p is 159 comma 114. I have chosen same value here, just to see it. 5 comma 200, 159 comma 114. By applying point addition operation here, we have to do. So yq minus yp divided by xq minus xp mod p. So the lambda value arrives at 194, and by applying, because only for point addition and point doubling, lambda equation alone is different. XR and YR equations are same. So XR value is 125 and YR is 152. So therefore the point 6p is 125 comma 152. Now as we have done 2p, we have calculated 4p, we have done 6p, again 7p, because the first window is 111 in binary, that is 7p. 7p is very important, because from that only we can begin the multiplication process. So 7p, how can you compute 7p? 7p can be done by 4p plus 3p, or 2p plus 5p, or 6p plus p, right? So here I have done 6p. So what I will do is, I will add 6p plus p. Again one more computation. So 6p is 125 comma 152. I'm going to use it here for the point p 2 comma 2. The equation that should be used, yq minus yp divided by xq minus xp. that is 2 minus 152 divided by 2 minus 125, which gives me a lambda value of 99. With 99 square minus 125 minus 2 mod 211 gives me 179. The XR needs to be used for calculation of YR, which gives me a value minus 12 mod 211, that is equal to 199. So the point generated for 7p is 179,199. So I use the 7p for initialization step, which is the first step during the multiplication process after the completion of pre-computation. So what you do, you first store 2p, 4p, 6p and 7p in a lookup table. Now you can begin the multiplication process. So initialize value, first this step, very first step in algorithm is S equal to N2 into P. N2 is 7, N1 is 4 and N0 is 1. As per the scalar 121 we have chosen. If the value of scalar chosen is different, accordingly this value will be different. So round 1, so after initializing S equal to 7p, we do the point doubling operation. Why? Because first 3-bit over. Next, for the next 3-bit, for every bit we have to perform one point doubling operation. So for point doubling operation, 3xp square plus a divided by 2 into yp mod p, apply it, you get the lambda value equal to 83. Because point doubling, what was the point? You have the point computed for 7p needs to be used here, because same value resulting from previous step needs to be doubled. Okay, so every result of previous computation needs to be doubled. So 179 and 199 are doubled. They will give a value 201,85. So second point doubling we have to perform. For second point doubling, take 201,85 as the point P and point Q. So when you double the point 201,85, you will get a value, a point 64,194. Right? How many times you have to double? You have to perform the point doubling process thrice. If the window size is 4 times you have to point double. So 194 is going to be used now. Again point doubling. So 64,194 will result in a point 137,174 at the end of the third point doubling operation. So after performing that, now N1 into P we have to do. So previous result, that is S resulting from the 3 times point doubling needs to be added with N1 into P. N1 into P was already computed. What was N1? N1 equal to 100. Right? Just look at this slide. In the problem statement, we have split it. N2 is 111. That is the first 3-bit of N. Next 3-bit of N is 100. So N1 into N2 into P was performed. The values were generated and stored in memory or lookup table. Again 100 into P, that is N1 into P. Now I am going to use it. So N1 into P comes here. So what was the value of 4p? 4p is equal to 159,114. See, now I used the point Q as 4p. Previous result 137,174 needs to be added with 4p, right? 159,114, which results in a point 116,114. Accordingly, you apply the lambda value. Because as I already told you, for point doubling and point addition operation, the computation of XR and YR remain the same. Only the the formulae for lambda are different. Now this completes the second window operation. Now for the given chosen scalar, we have to perform 2 window multiplication operation. After that, only one final bit computation, final bit multiplication. So the final bit is 1 here, as I already told you. If the final bit is 1, you perform 1 point doubling and 1 point addition. If the final bit is 0, perform only 1 point doubling, because the value is 0. So round 2 is for last operation, that is 1 point doubling operation. The result of previous round is 116, 114, and now I have to double it. So when we perform point doubling operation on 116, 114, it gives me a value 115, 163, right? So the value is 1. Final bit value is 1. 111, 1001. That is n value equal to 121. What is our objective? We have to perform ng where n equal to 121 and g is equal to 2, 2. 121 into 2, 2. We are performing now. And we are in the verge of completion of multiplication process. So point addition operation is equal to s plus n naught p. What is n naught? N naught equal to 1. Because only one bit. N naught into p is equal to p. So s plus p we have to perform. What is p? The point is 2, 2, right? So 115, 163 needs to be added with 2, 2. Just read p as g. Don't confuse with the p that is mod p. The p value mod it works in the prime field of 211. Now read p as g. The point. The point is what? Point is 2, 2. Now 115, 163 needs to be added with 2, 2, which results in the final value, final multiplication output as 115, 48. And I hope you remember that the same value was obtained for our left to right scalar multiplication. Now we are also obtaining the same value, right? So that ensures that all the pre-computations plus multiplication processes have been performed in a very proper manner. Now, the total number of point doublings, as we already analyzed that, total point doublings is equal to 6, including pre-computational overhead, and total number of total point additions equal to 4, including the pre-computational overhead. So I observe there is no change with respect to number of point doublings and number of point additions as in the case of left to right scalar multiplication. We cannot always expect that Windows multiplication process must result in reduced computational overhead, because as I already told you, if you are doing this continuously, then you can avoid lot of pre-computations. Only corresponding doubling operation most of the times you do, so that the addition operation especially required for that can be minimized, right? So in this lecture we understood how windowed scalar multiplication is used for scalar multiplication, and I hope you have understood it in a clear way. Thank you.